Okay, welcome you all to this lesson on Newton's laws of motion. Sometimes, as we go through our career, there is a need for us to keep revisiting our basics and brush up our basics. Not that we are going to forget, but it's a good way to keep ourselves afresh in revising our ground subjects and associated knowledge, etc. Anyway, so this lesson is about Isaac Newton's laws of motion. Of course, this could be useful to the high school students and those who are aspiring and those who don't have a very strong science background. So it's going to be helpful to them. To start with, Sir Isaac Newton lived between 1642 and 1727, and he propounded the laws of motion, and which he published in a book called Principia Mathematica, and which forms the fundamental plane on which all our other knowledge, physics and physical world phenomena and knowledge about that thereof has been built on. So you can say he is one of the earliest person who gave a direction, and that also very good one. Okay, even though the subject is very familiar to most of us, we will take step by step explanation so that maybe for a student of a high school student who goes through this lesson, he will be able to benefit out of that. Okay, prior to Newton days, the concept was slightly different. That means if a body was not in motion, if it was rest, it was understood, it was perceived that no force is acting on it. So it is continuing to maintain its state of rest. If they found an object moving, then it was perceived that a force is constantly acting on it to make it continuously move. This was the idea which existed prior to Newtonian days. That brings us to the Newton's first law of motion, which defines the basic property of inertia, which changed the earlier notion of what I just covered. The the statement of the law itself states a body continues to be in a state of rest or uniform motion unless operated upon by an external force. Here, as you can see, that uh, the concept entirely changed. That means what Newton tried to do, he defined a residual force in such a way that it will cause the either change in the particular status of uniform rest, I mean state of rest or uniform motion. That means if a body was continuing to move, it just means that it doesn't have any residual force. We will be seeing this in more detail in this particular lesson. Okay, let us take step by step. Here I have shown a block which is resting on a table. This is a body at rest. Does it have any force acting on it? As per Newton's first law, no. And also, I have tried to show a plane which is flying at a uniform motion. As you can see, it is not changing its speed; it's maintaining its uniform motion, uniform speed. Does it have any residual force? Once again, no. This is what is being defined by Newton's first law of motion, and we are going to explain further. Okay, as we proceed further on on this law, I want to explain something. When Newton defined saying that a body continues to be in a state of rest or uniform motion unless operated upon by an external force, as I told you, now it should not be perceived as if no force is acting on the body. It is on the contrary. What Newton tried to mean, or what he tried to explain, is no residual force is acting on the body. That means sometimes that force, there are forces acting on every body. That is something which you can't help it. As long as there is no resultant and residual force is not acting, then a body continues to maintain its inertial status. Like here, the block which is resting on the table, there is one force which is trying to pull it downwards. That is the gravitational force by which it owes its weight, etc. And there is an upward force which is exerted by the tabletop of the body, so which keeps it at that particular position, and these two balance out and there is no residual force. Similarly, when the plane is moving, there are several forces. That means there is a forward force, there is a rearward force which is called the drag, as you would have learnt in your aerodynamic classes. There is an downward force which is the weight of the plane, and there is an upward force which has to balance out this particular weight of the plane. So as long as these all the forces are balancing out and cancelling out and there is no residual force, then it continues to maintain its state of whatever speed it was maintaining. Okay, what do we understand after learning the Newton's first law of motion? What are the concepts which we learnt? Which we understand the concept of a body at uniform motion or uniform, present state of rest. It defines the property of inertia or the property of mass of a body. Okay, mass is the measure of inertia. More the mass, more the inertia, more is if a body has a bigger mass staying at rest, it will require more force. So that's the measure of inertia. This law gives the quantitative definition of force, that is the net force. So it is often referred to as law of inertia. And in the larger frame, you could say Newton tried to establish the inertial frame of reference for all his further laws. Though it appeared it's a simple one sentence, but I'm sure he thought over it in great detail and he took this as a fundamental principle to define the frame of reference. As you would go further in further deep in physics, because there are different frames of reference in which these particular laws may not be applicable. That's the point which I would like you all to understand. So but this gives a very very good understanding to start with, to understand motion, to understand mass, to understand. It forms the basic of our physical world understanding. Okay, as professionals, we can't stop at this. We have to understand the mathematics of these particular laws, which I've tried to explain. Here, what I have explained is this will read as Sigma f is equal to 0 implies dv by dt is equal to 0. Sigma f will mean sigma f will mean the resultant force. What it means is, as long as the resultant force is equal to 0 dv, then there is no change in velocity over any different timings. That's what this particular expression means. If there is no change in velocity over a different period of time, would mean if the body was at rest, it continued to be at rest. If it was traveling, say, at a particular speed of 30 kilometers an hour, it continued to travel at 30 kilometers an hour. That's what that means. The delta v is the change, and there is no change in speed over different change in timings. That's what it means. This brings us to the concept of momentum, which is enjoyed by the body. If a mass is traveling at a speed or velocity of a particular velocity, then the momentum is defined as the product of mass into velocity. Okay, let us get on to the Newton's second law of motion. From the first law, we derived the concept, basically, we derived the concept of inertia, mass, and which we related this mass and velocity to inertia, and we called it that momentum. So now we are going to define and refine this concept further. Newton's second law in this law, we are going to define the force. Rate of change of momentum is directly proportional to the net force acting on the body and takes place in the direction of the next net external force applied. This is what is very important. That is, it takes place, the change of momentum takes place in the direction of the force applied. That's what we are going to take up for further explanation. Okay, let's go through the mathematical explanation because we are professionals. Now, here we try to explain the concept of force. Here we have shown delta P over delta T, that is any change in momentum over a period of change in different time. That's what we are trying to define. That's what defines the force. That's what is the concept of force. If there was any changes in this momentum, will give you a change in will give you the concept of force. Let's get down, which means this force is proportional to delta mv upon delta t. So, but of course, there is mass is not changing, right? Mass is remaining a constant for in the physical world. So the whole thing will be written as mass into delta v by delta t. That means the momentum change takes place only in terms of velocity of that particular object. So dv upon t, which is called the acceleration. That's what we want to define by this particular law. So F is proportional to mass into dv upon dt, which is called the acceleration. Or if we introduce a constant, or if we define our units in such a way that there is no constant which is involved, it becomes force equal to K into MA, or force is equal to MA. This is a very important equation which we will need to understand and which we will continue to use in all our numerical examples in our future mechanic lessons. Okay, we defined an expression for force up to the Newton's second law. Let's get on to the third law of motion. It simply states to every action there is an equal and opposite reaction. So it's a very simple concept. Once you have understood law 1 and law 2, the third law is an automatic fallout of the number 1 and number 2 law. Of course, we are going to see it in a little bit detail uh, to improve our understanding. All right, let's continue. Action, reaction, and the force. When two objects interact, the force exerted by one object on the other is equal in magnitude and opposite in direction to the force exerted by the latter object of the former. That means you try to push an object, the object is equally exerting equal force on the backward side. That's what it means. That's how uh, the physical world maintains in some particular equilibrium status. Otherwise, it would have been chaotic, right? So we will explain this further. Okay, action reaction. Yeah, I've just tried to show that the book is resting on the table, and the book, because of its mass, it's exerting a force on the downward direction, being pulled by the gravitational force, and the tabletop surface is resisting it or exert an equal and opposite force. Therefore, this book continues to remain static on the table. Okay, just trying not to restrict only to the Newton's law of motion. I tried to extend this lesson by introducing ourselves to some more concepts, which we will prepare ourselves to learn our mechanic concepts in our future lessons. To start with, the first concept I want to know. Let me remind you, all these concepts are fallouts or derivation of the Newton's basic laws of motion. Anyway, impulse, a force acting for a duration of a time, or the product of force and time, and its unit is in kg meters per second. That means if an object comes at a fairly good velocity and comes and hits, let's say, a surface, a wall or something, a ball which you throw and goes and hits on a wall, when it hits the wall, it acts. There is a force which is exerted on the wall for a particular duration of the time. So, this is called impulse. That will take me to another fundamental concept of law of conservation of momentum. In an isolated system, the vector sum of the momenta of bodies remains constant. These are all interpreted again from the Newton's laws of motion, which only means that it is maintaining its current status. That's what it actually means, which means that if there was any change in status of that particular body, then we need to understand that there was a force which was a residual acting on the particular body. Otherwise, it wouldn't have changed its status. That's what we need to understand. Okay, a lesson is never complete unless we have gone through some numerical examples. Let's do a simple numerical example on impulse. And before getting on to the actual lesson, uh, let's say this may not be practically, it may not be true, but to understand the concept, I have given this particular numerical. A sphere of zero point 0.5 kg strikes a wall at 15 meters per second and bounces back at the same speed. What is the change in momentum of the sphere? So we learned that a change in momentum is mass into velocity is so it was traveling in a particular direction at that particular speed, say 15 meters per second. So its initial momentum was zero point 0.5 into 15, that is 7.5 kg meter second upon second, but it is bouncing back at the same speed. So the present momentum, that means in the reverse direction, will be the same, that is 0.5 into 15 meters per second, which will be 7.5 kg meter upon second, but in the opposite direction. When you change, when you want to calculate the total change, A minus B, so there is a total change in momentum of 15 kg meter per second. Okay. Of course, this normally doesn't happen. Normally it doesn't happen. The ball, when it strikes the wall, a sphere, when it strikes the wall, it is going to lose some energy, and the reverse force is not going to cause the sphere to travel at the same speed. Therefore, if we knew the speed at which it is traveling at the reverse, then we are able to calculate the loss of momentum because of the sphere striking the wall. That's what I want you to understand, explain in this numerical. Okay, yet another numerical example. A ball of mass zero point 0.4 kg starts rolling on ground at 20 meters per second and comes to a stop after 10 seconds. Calculate the force which stops the ball, assuming it to be constant in magnitude throughout. Now, before I proceed further, in all our examples, all our study of motion, we would be dealing a case where the acceleration or deceleration is uniform. That means the rate of change itself is taking place at a constant pace or constant rate. If the rate of change of acceleration itself were to vary, then we are getting into a little bit complex issues, for which Newton, of course, came out with calculus. So we will not go into that. Let's get on to this numerical. Mass is 0.4 kilos and initial velocity is 20 meters per second. Final velocity is 0. Therefore, acceleration is a change in velocity, we learned, right? 20 minus 0, and it has taken, it has stopped over a period of 10 seconds. So 20 minus 0 upon 10, that is, it has decelerated at the rate of 2 meters per second. So the force is mass into acceleration, that is 0.4 into 2, that's equal to 0.8 meters per upon second square. This is what it means. That is, the unit of force is Newton. So force is equal to mass into acceleration, 0.4 into 2. So it is 0.8 newtons. That's what it means. We come to this end of the lesson, which is the basic introduction lesson for further studies on mechanics, etc. I hope you found this lesson interesting, especially the numerical examples. You may have to sit and little bit spend some time working on the examples. Then you will gather much better understanding on the subject. I thank you all for going through this lesson. Please feel free to offer your comments and surely follow my lessons in my YouTube and my website channels. Looking forward to presenting more and more lessons. Thank you very much, and if you found this lesson useful, please forward it to other high school students so they will also benefit out of this. Thank you once again.